Hello and welcome back. If you follow the channel, you know that we just repaired an HP 9895A dual 8-inch floppy drive. And we immediately rewarded ourselves with a round of Colossal cave on the HP 9825 calculator. But I brought back 3 more of these from my 2019 loot in Los Angeles. You know me, I want to repair them all. But this round will prove to be quite challenging, as we are going to have to pull out the logic analyzer and the team's best brains to deal with some misbehaving controller boards. So I thought I was cooking. Here's the first disk that we repaired, works fine with 9825. Then I went to restore 4 more drives. I made another complete disk unit, this one works. And then I made a third one. And this one I thought would work because it passes all the internal tests. Yeah, it's fine. However, when I hook it up to the HP 9825, it hangs the machine. And it turns out it's not the drives, it's the control board. This one didn't come with a control board, it was empty, but I had a few spare control boards that I picked up from the same place. And I tried this one, it didn't work. I tried the other one that's in there right now, it kind of works, it passes internal tests, but it breaks the 9825. And if I put one of the good boards, it works. So now we have to debug one of these boards, which has 2 complicated chips in there. It has the Phi chip with the GPIB, which appears to work because I can give it commands, and there's the Z80, which appears to work too because that's what drives the whole self-test, and that works. And there's a C of TTL in here, and there must be a fault somewhere, and that hangs up the machine as soon as I want to do a read or a write. Alright, at this point we already need our first bout of elevator music. The disk controller responds fine to some commands such as dtype, which returns the type of disk in the drive. Here it tells me 2, which means that it found a diskette and that it just had been inserted. A lot must be working right on the controller card for this to happen, which is good news. But when I try a cat, short for catalog, the disk directory command, the HP 9825 goes into a coma, then returns an error D8. But D8 simply means hardware failure, which doesn't give me much to go on. To know what happened, I need to sniff the traffic between the computer and the disk controller. The HP 9895 was one of the first diskette drives to implement an HP proprietary disk access protocol over HPIB, known as Amigo. Think of it as an early precursor to SCSI. HPIB, recognizable by its stackable cables, was an advanced interconnect for the time, capable of 1 megabit per second transfers in a multi-addressed, networked environment, which was pretty wild for 1972. It is still with us many years later, standardized as IEEE 488.2 and now known as GPIB. But only the instrumentation communication part has been standardized, and not the high-speed mass storage protocol that HP used. Fortunately, the protocol used by the HP 9895 is one of the very few instances where the Amigo commands have been documented in full detail in the service manual. Here is a list of all the commands supported by the disk. So if I put a logic analyzer on the HPIB bus, I should be able to recognize these low-level Amigo disk commands and, hopefully, single out which one led to our failure. So I first tried to debug it with my ancient HPIB bus analyzer, but that wasn't enough. It has only 30 positions of memory. So I had to hook up my more potent 1670G analyzer through this little interface, which is very nice. You put GPIB one end, the probes the other end, and it even reverse assembles the result. And then now I have whole traces of the very verbose interaction between the computer and the disk. So I'm going to try to exercise the drive back there in the rack. That doesn't work. So it's the left one, and it's at address 5. So it's drive 0705. And if I do something simple, actually, let's get a trace on this. So I'll go over here. I'll do run. And now it's waiting for the stuff. And then I'll do execute. And it answers 2, which is the correct answer. There is a disk in there. So we'll stop the trace here. And here I can see my trace, and I'll actually print it out, so it's going to be easier. Print all. And out it comes on my ThinkJet. We are doing it like it's 1985 all over again. And Ken is going to help me figure out what's wrong with the Z80. You have reverse assembled a lot of Z80 in your life?
Well, not a whole lot, but someone else disassembled the ROM, so it should make it a lot easier for us to see what's happening when we look with the logic analyzer.
Okay, so let's see what happened here. Oh yeah, so this is just so that the bus reads in the correct direction, that the controller is listening. And this is a special command. It's called an identified. So that one is identified. And it responds 0081, which means it is a 9895 disk. This is a DSJ. DSJ is air check. And it says O2. O2 is power up. So it's been just powered up, so that's correct. 6A03, that is a give me status. So it's status request. Then you reverse the bus. Now the controller is listening at 21 and the talker is the disk at address 5. And then you ask it, give me results. And then it gives the results. And I know this tells me it recognizes as an HP disk two-sided in it. It's also first time it reads it, so that's all fine. Good status. Then it's still asking something from the device. Yes, it's doing a DSJ, and now it should respond with 0, no error. Yeah, so DSJ number 2, 0, 0. Okay, this is another 6A03, so status request, and it's getting now 00OC00, which is I am good, I have a disk. The disk just inserted thing went away. Oh good, this is completed correctly, and I'm going to do a cat, which is just the equivalent of directory. So I list once what's in the disk. And we'll try to record that, and that I bet you is gonna fail. So it started, I heard the disk load the heads, and then it's hanging up and gives me an error D8. Okay, and then we'll see what has happened. We'll stop it. Okay, so it didn't go very far. It's requesting to, so the 60, this is seek. So now we're getting into the thick of things. It's seeking to 17. Can't remember what the 6A05 is. Oh, it's a read data. Oh, then it's reading sector 17 and it gives me the right result. Null equal DC1W, it went to the correct place and read the sector. The rest of the directory should be empty because I only have one file. So it read from the disk. I'm pretty surprised. So it got its directory thingy. Oh, you can see at the end. Alright. So I have 4 parallel polls in a row, which means the Z80 didn't respond. And then eventually it just gave up. So good news, we caught it in the act at the very first try. Bad news, it fails in a really mysterious way. It goes through a very long sequence of commands, seeks to the proper sector, reads the data correctly, then fails on a very simple status request. It looks like the processor on the disk controller just hung. which is particularly puzzling because this status request completed without problems many times before. To make it worse, it's not repeatable. Sometimes it completes many actions before it fails. Sometimes it fails on the first status request. That's going to be a real head scratcher. But this is super hard to debug because there's a ton of transactions and I just want the one that fails. And in order to generate the little bit that fails, the best that I have found is to use the HP85 and I have a little program that exercises just a few HPIB commands I want. So now I am switching gears, or more exactly switching computers. I'd like to send a few particular Amigo commands out of that long sequence to try to isolate what makes the disk trip in a more repeatable manner. The HP9825 won't let me do that easily. However, the HP85 is a dream machine for that. It lets you send any arbitrary HPIB command using simple basic statements, which I can then wrap in a simple user interface in a fraction of the time it would have taken me to do it using modern ways. So on the unit that works, I think I have it down to a T. I can read error status, that's called DSJ, and tells me 0, no error. Then I can read the detail status, which is all those 4 bytes, so that's fine. I can seek to some place. Let's do cylinder 40. Ta-da, I go seek. I heard it. So that's working fine. However, if I do it on the other unit, it will hang. So for example, on the bad drive, I can just hang it by requesting status. Status works the first time. And now I'm going to try to see what happens. I do status for a second time. Did it work? Oh, now it works. DSJ. Ah, there you go. Caught it. So we go here. And I just have a few transactions now. Then we'll print that out and figure out what was wrong. So this is a correctly formed status request and it responds with a status here, which is 00OC00. Then I did it a second time, so it worked. I did it a third time, it worked. And here I did something different. I pressed the DSJ button, and then when I did the status sequence again, it just hanged, it responded nothing. Which tells me that we need to get a level deeper. It's whatever the Z80 processor does that's wrong. The HPIB interface chip seems to work. It can handle a conversation. And it's inspected the board because we're about to go to one level deeper where we have to instrument the Z80. But Ken, you found that by some miracle it's going to be easy to hook up to it?
So yeah, this gives you all the Z80 data address control line. I mean, this will give us enough to follow the disassembled code and see what the Z80 is doing.
Okay. Well,
so we only need this bus connector.
Right.
Yeah, and guess what?
Yeah, look at that.
I have made one. There you go. And another thing we were thinking is just, I was thinking the same, maybe the RAM is bad, and I happen to have 2 extra RAM chips. So
2114 SRAMs are known to go bad.
And it looks so weird that
well, it's unstable, so
right.
Sometimes it'll work and sometimes it won't.
So bad RAM could be one. So we want to just change the RAMs first and see if that does anything before we go and
it's a bit of a shotgun, but it might be worthwhile.
Yeah, it seems to work pretty well for bad RAM. Like, reading the right data, and I would expect things to go worse, but you never know.
Those are 2114, 4K static RAM, 1K by 4 bits. Okay, another one. They are resisting. We're going to socket them because it's memory. And then we're not sure if they're bad. We'll get one new old chip. Yeah, 2 new old chips. Okay, new board with new RAM in there. And if it's going to start, we're going to see the LEDs. Yeah, it's starting. Okay. So at least we didn't break anything. Okay, let's see if that give me anything. Okay, it responds. Status. ESJ. Read. It reads the data.
Nope, no good.
Nope.
So that was not the issue.
Okay.
Alright.
And same thing, it's random hang. Oh well. Okay, so full instrumentation after lunch.
Sounds like a plan.
Alright, back from lunch, it wasn't the RAM, so it's something more complicated. So I added another pod to the logic analyzer, hooked up to the Z80 signals, which were conveniently available from the front test connector, and set loose the Eric and Ken Dream Team on the
Just
problem.
going to run off end of
And we have the trace, we have the address, what it's doing, and then thanks to Craig Ruff we have the code, and you guys tell me that it's not doing what it should already.
So basically it's trying to find the command in this table of justified commands.
Right.
And it keeps not finding it. It's running off end of memory into all zeros.
So it went outside of its table?
Yeah, it's like outside of the ROM, it's outside of memory, it's like off.
And it
in
only does that
the
on some
wilderness.
specific commands, right? It's really bad address bit or something. A bad
be a
IO
lot of-
bit.
I think we should trace and figure out where it first goes wrong.
Okay.
And see what's
Count me in.
happened.
Alright. Let's do it.
A few minutes later.
You bunch of geniuses.
Trigger.
You've come to realization that it's looking for a secondary command value that doesn't exist.
Yeah, it should be looking up 8 in the table, but it's looking up 48 in the table, which doesn't exist. So it just runs off the end of table into code, into empty memory, and infinite loop time.
So I should maybe explain that. If I take the HPIB traces here, yeah, what I am sending it sometimes, well, actually every command has a secondary. Here's secondary 68. The 6 is actually not part of the secondary. The actual secondary is the first 5 bits, so it's 8. And that's what it should have been passed on to the processor. And somehow, instead of getting 8, got 48. Is that what you think happened?
Yeah.
And then you can see, then it stops responding, and I think we caught the Z80 in the act trying to figure out what 48 is, and
It goes
should
through
have.
all its command tables, and it can't find 48.
Yeah,
it just
because
doesn't exist.
and I
Doesn't exist in code,
I
doesn't
sent it an 8, right? So something got lost in the transaction, and that would explain why the board works. I was able to read complete sectors out of the thing, right? But it just wouldn't hang on certain commands.
So data corruption somewhere.
Yeah. Ooh. So now difficulty is to try to find exactly where it goes wrong, because we capture megabytes of data.
So it's
48,
checking
48.
48 from the FIFO. Wait a minute, is that a... I guess that's a read. I can't tell if that's I/O or not.
Yeah, IO request. Yeah, you have it right here.
Oh, okay. So is that a active high?
Yes, everything's active.
Okay, so this is the I/O address. So it's reading 48 directly from the PHY.
Oh, Phi is giving it the wrong bit, or has some bit stuck.
Yep. It doesn't sanitize it. It just passes it directly into the table.
Why wouldn't you trust the PHY? It's an HP chip.
It's an HP chip.
Oh boy.
The Phi is that
So I
very hard to find chip right here.
don't see any sanitizing.
Okay, so it gets past the wrong data straight from this chip. Do we just change the chip first?
Well, we could.
We could take a good trace just to make sure that.
Okay,
Obvious
good trace
solution.
is a good solution. Oh my, a buffer overrun uncovered by a hardware fault. To make double sure, let's check on a good board. We should see an 8, not a 48. And we put a good board in the disk, which now behaves, and now we can do a good trace. And your suspicion is confirmed.
So line 5 here, 08 is the good byte. On the bad board we see 48.
So the Z80 is given a bad byte by the Phi,
By the PHY, it tries to find it in the table,
and
it can't. So it
and the
just goes-
code you're not very impressed with it, because you should have checked against bad
yeah,
byte.
they're,
Right?
they're not checking array bounds or masking off. So if it's a bad byte, it's just going to go off into the weeds.
Okay. Oh my, that's a horrible fault that our dream team just uncovered. Our PHY chip apparently passes an invalid HPIP command to the ZAT, which is off by just 1 bit. If the ZAT had properly written code, it should just respond with invalid command and report an error. But there is an awful bug in the code, so it merely continues its lookup outside of the command table, and there you have it, buffer overrun. That's a horrible programming mistake, unfortunately still prevalent in modern software. It's what hackers use to break in modern systems. Scary, scary bug. In modern days, we'd immediately and secretly report the bug to HP, which would work on a fix, distribute it, then issue an alert after it had been fixed to prevent exploits. But in our case, we hope no one is interested in hacking into our 9895, so we're just going to change the PHY chip. Okay, so we know this chip is giving bad information to that chip.
No, that's the good board.
Yes, it's metaphorically speaking. So we want to switch the 2 chips and see if the fault moves with the chip,
Brain
right?
transplant.
Oh, I missed that. Look at what Mr. Fancy Pants has done.
Oh no.
I missed the exchange, but we exchanged the
again.
2 PHY chips on that. And, well, which one do you want? You want to good board with the suspect PHY chip? See if that works.
Yep. And then we can either vindicate or convict the PHY chip.
Sounds good to me.
Okay, so that's the good board with the suspect PHY. Let me run a few DSJ because you need to status. Nope. We made it. We made bad PHY chip.
Okay.
It failed on status. Well, let's see if we conversely we made the bad board good. The bad board with the 500 formerly good board.
Yeah,
so if we make it, if we repair it.
And if not, we've broken both of them.
That's a distinct possibility. That's the bad board. That's in there now, and then we can see if we made it good. It's running DSJ status. Status, DSJ status. I think we repaired it. Let's do a read. It's reading fine. Let's do a next read. Still reading fine. Let's do. Now I do a seek.
Yep.
Yeah. Okay. Bad PHY chip.
Okay.
Excellent work.
Woo! And then now we'll do one more rotation of this bad board where the ZAT doesn't even start to this other bad board.
We should check all the chips.
Actually, we don't know. We don't know if the ZAT doesn't even start. It never went into self-test, so we assume the ZAT doesn't work. But oh man, this is tough.
So you're going to take that PHY and put that in the good board and then make sure that it works still.
There we go. It's a 1AA66004. Alright, so that's the bad board, which we know is due to the bad chip, with this chip from this even worse board. DSJ status, DSJ status, it works.
I see.
Can I read first? See if it reads. I like to, okay, it reads correctly.
Read is boring.
Cylinder 76, right? We just have no fear. Seek.
Yep.
Alright, okay. So
Awesome, it works.
this board has now a bad processor and a bad PHY chip. Okay, so but at least we have 3 drives running. And I don't know if we want to spend some energy on that one to see what's
Well, we have the
bad.
logic analyzer set up to analyze the CPU, so might as well.
Yeah, I think that makes sense.
Okay, alright, well, progress. Okay, last board, now it has the bad PHY chip, but we know that if the ZAT would work, it would at least do self-test, so we're going to try this one, but my hopes are not too good. Alright, okay, so absolutely bad board with absolutely bad PHY chip.
What if it works?
Table.
2 wrongs make a right.
Well, we
3 lefts do.
So that one, I'm not expecting anything out of it. I think the lights will all go all red. Yeah, that's what it was doing before. So Zippo, nothing. Do you see any activity?
Stop it, I think.
Nothing.
Okay, that is super dead. Can you tell if the clock is running?
I think it is, otherwise it would give me a warning that says waiting for clock. We could try and get a reset pulse on the Z80 to see if it tries to fetch anything at all.
Okay.
It could just be it's stuck and...
Alright, you know the switch.
Hang on 1 sec. Go for it.
It's not going to do anything.
Yeah, I don't think so either.
No, it's lifeless. Well, you know, this one we can take it out of the machine and power it with 5 volts and see if it's running with a scope or something. And this is board number 4, for which I don't even have a good Phi chip anymore, but I just can't stand to lose a board from HP. So I try to power it up on the bench. That's the one that doesn't come up, and I can't even do it with my power supply. It sends it to 2 amps, almost 1.7. So it appears that it is shorted somewhere. That would be my guess. That's why it doesn't start up at all. Actually, I see there's a lot of S logic, 74 S logic on it, so that's very power hungry. So maybe 2 amps is normal. So I put it on my little stronger power supply. Okay, 2 amps. And still doesn't do a thing. We have clocky, so that's not the problem. Any activity anywhere? No. Read is stuck in the middle at 1 volt. Refresh, it's just completely lifeless. It should refresh at least. We have clock. We sure do. And it's not held in reset. Reset, yeah. The reset is working, I saw it coming. Okay, so I tried the obvious, get the Z80 out, put a new one in. And it's still 2 amps, and it still doesn't... Ah! No, it started this time. Okay. Okay, we have some life out there. Alright. And then now I put the plus 12 volt in, and we have even some more action. We have action. Processing action. Yep. And I guess the ROMs are... The ROMs are hot, but these are older ROMs, they're PROMs actually, so I'm not too worried about that, and they're all hot the same. So this board still runs at 1.9 amps, but maybe that's not too far from the normal. The other board runs at 1.5 amps, but instead of having 4 hot PROMs, it has one very cool mask ROM, so that might explain the difference. Alright, so we'll put it in and see if that revived it. Let's see if that's enough to revive it partially. I don't know if we want to take traces of it, but let's... Yep. It's up. Okay, let's see if it responds to commands. Don't do too many because he has about 5 chips in it, but it looks like we revived it. Alright, and run. Yeah, identify DSJ, and I suppose if I DSJ is fine. If I run a status, oh yeah, it has the same error as before, drive unresponsive. So I bet it's repaired too. We just have a bad Phi chip on that one. I guess if I can find a Phi chip, then I'll get 4 working 9895s.
Silicon-on-sapphire chip to intermission.
And of course, while we were looking for a replacement good Phi chip, Ken could not resist opening the bad one up, looking at it under the microscope and reverse engineering it. It's an absolutely fascinating and very odd chip because it uses silicon-on-sapphire technology. You heard right, the substrate is not silicon, it's transparent sapphire, the kind that jewels are made of, just an artificial version. So you can see right through the chip. Here you can see the golden X at the bottom of the ceramic package going right through it. Of course, Ken succeeded in reverse engineering the chip and wrote a whole article on it, link in the doodly-doo. But here is a short tour by the master himself. Okay, so Ken, it took you like half a week to figure out the chip.
Well, the main problem was figuring out what the transistors are, because the transistors, the contacts, and the crossings all look the same, which caused me no end of confusion. The top of the chip is what connects to your microprocessor. The bottom of the chip is what connects to the I/O bus. You have some control lines and you have some address lines. Probably the most interesting feature is the FIFO here to buffer data between microprocessor and the I/O bus.
Can you make it bigger? This one, yeah, you'll have a much better picture.
So the two FIFOs are basically, each one is a static RAM cell, but the control logic makes it a FIFO rather than a static RAM, keeping track of where the data is going in and out.
And you were able to reverse engineer the cell even?
Yeah, it's pretty straightforward. Two inverters in a loop to store the bit. Then you have a transistor to put data in, and a transistor and inverter to take data out.
It's straightforward to you, but to us it's not. Right, there's a cell and it's straightforward, right?
So
you see transistors in there?
Yeah, so they're metal gate transistors. So you have the gray silicon and then you have the white metal on top. And so where it crosses the arm there, that is a transistor. You've got your power and ground buses here. So this blobby thing is an inverter. So you have two inverters, past transistors, and row select lines, data coming in vertically, and there you go.
Yeah, obvious. Actually, it's in your blog, right? You explain all of that.
It only took me a couple hours of, what on earth is going on here? What are these people thinking?
I am impressed because I can't make sense of any of this.
Another circuit I found interesting was the decoder. So there's 3 address lines to select 8 registers for reading and writing. And then this decoder here is what converts your 3 address lines into lines that go to each individual register. This register.
Oh, that is the interface to the processor, to the Z80.
Yeah.
Right, that wants to read and write to the chip, and it does that through registers.
Yeah.
All right.
So it's basically, you have your address lines coming in, and then the pattern of the transistors will match one of the columns, activate that column, and then the line goes off to the register to make things happen when you select that register.
And where is the register? Oh, I think the camera is going to turn off. He's unhappy with the battery.
So the registers, there's a lot of them down near the bottom of the chip. Slightly different because it has to do more stuff than just store the bit. But it's similar storage, and then the signal goes off to do something. And there's also a mini decoder here to select one of the 8 I/O lines, which you said was for the parallel pole.
Yeah, parallel pole is always hard to redo.
So you have three select selects coming in, and then 8 lines coming out. Then you have your I/O circuits, your drive transistors. So it looks pretty different from your normal CMOS because of the silicon-on-sapphire, and also because it's metal gate, not polysilicon. And because it's metal gate, you only have basically one layer for routing, which makes the routing a lot harder.
Super hard.
So there's a lot of wasted space where there's just wires going around. They go to a lot of work to avoid things crossing.
Can you show us an AND gate? You were able to figure out what an AND gate looks like?
Okay, if I remember where they're hiding. So yeah, here's a here's a NAND gate. Maybe I should kind of go more. So at the top we have an inverter, so you can see the two transistors in parallel, NMOS and PMOS. Both gates are driven by the same signal. Down here we have a NAND gate. You can see the two NMOS transistors in series here, and the two PMOS ones in parallel here. So, it's basically your typical CMOS construction. It just looks different.
So these are the two inputs then?
Yeah.
These are the input lines coming in, and then you've got 4 transistors total, and then this would be one of your power rails, and presumably this would be the other one?
Exactly.
Okay. And then the output's going to be in the middle.
And then the output goes to the inverter.
Aha.
Well, thanks, Master Ken, for the enlightening masterclass. In the meantime, we received our replacement chip, so let's go back to our repair.
End of chip tour intermission.
We found a Phi chip. It was from eBay. It said new, old stock, but it's not new. As you can clearly see, it has the marks of the clip. So it was pulled from one of the equipment that this guy repaired. So hopefully the equipment was bad, the chip was good. We'll see. To be honest, it would have been a miracle if we had found a new one. Pretty much the only way is to pull them from old equipment. Fortunately, that chip was pretty widely used. Alright, so let's see if that will finish the revival of our last board. Alright, try this again. Initializes properly. Let's see if the new Phi chip did it. Identify. Yes. It's not making any errors. It's talking to us. Status. Got it. Seek. Did it. Cylinder 40. No problem. Can we read? We can read. Okay. So it's repaired. So we got a good Phi chip from eBay. So we have 4 good boards. 3 good frames. I have to repair 2 more drives, and I'll have 4 good frames. That shouldn't take too long. And voila. Much better. Okay, so we now have a grand total of 4 discs, 3 over here and then 1 next to the HP85. And this is the one we just repaired, last one. That's good. I made an effort. I even repainted where the paint had faded. So, woohoo! Looks all pretty. I'm the one with the most HP 95 that still works, I think. Alright, see you in the next episode.